Welcome to the fascinating world of solid-state in chemistry. In this video, we'll explore what makes solids unique among the three main states of matter. Solids are all around us, from the chair you sit on to the salt in your kitchen. But what exactly defines a solid at the molecular level? Let's begin our journey by understanding the basic characteristics that set solids apart from liquids and gases. We'll see how their rigid structure and fixed shape are a result of closely packed particles. Get ready to uncover the secrets behind the stability and strength of solids as we dive deeper into their chemistry. Solids are defined by their definite shape and volume. Unlike liquids which flow or gases which expand to fill their container, solids maintain their form. This is because the particles in a solid are tightly packed together, often in a regular, repeating pattern. This arrangement gives solids their rigidity and resistance to compression. Whether it's a diamond or a block of wood, the underlying structure is what gives each solid its unique properties. Let's look closer at how these particles are arranged and what that means for the material's characteristics. At the microscopic level, the particles in a solid are arranged in a fixed, orderly pattern. This regular arrangement is known as a lattice. The particles vibrate in place but do not move freely, which is why solids retain their shape. The strength of the forces holding these particles together determines how hard or soft the solid is. For example, in metals, the particles are arranged in a way that allows them to slide past each other, making metals malleable. In contrast, the rigid lattice in diamonds makes them extremely hard. Solids can be classified into two main types, crystalline and amorphous. Crystalline solids have a highly ordered structure with particles arranged in a repeating pattern. Examples include salt, sugar, and most metals. Amorphous solids, on the other hand, lack this regular arrangement. Glass and plastics are common examples. The difference in structure leads to different physical properties such as melting points and how they break. Understanding these types helps us predict how a solid will behave under different conditions. Crystalline solids are known for their well-defined geometric shapes. Their particles are arranged in a repeating three-dimensional pattern called a crystal lattice. This regularity gives them sharp melting points and allows them to cleave along specific planes. Common examples include table salt, quartz, and diamonds. The beauty of crystals lies in their symmetry and order, which also contribute to their unique optical and mechanical properties. Let's explore how these lattices are formed and why they matter. Like crystalline solids, amorphous solids do not have a regular repeating arrangement of particles. Their structure is more like a disordered pile, which is why they don't have sharp melting points. Instead, they soften over a range of temperatures. Glass, rubber, and many plastics are classic examples of amorphous solids. Their lack of order gives them unique properties, such as flexibility and the ability to be molded into various shapes. This makes them incredibly useful in everyday life. Crystalline solids, the smallest repeating unit is called the unit cell. Think of it as the building block of the entire crystal. By repeating this unit in all directions, the entire structure of the solid is formed. The shape and size of the unit cell determine many of the solid's properties, including its density and how it interacts with light. Understanding unit cells is key to grasping the complexity and beauty of crystalline material. There are several types of unit cells, each with a distinct arrangement of particles. The most common are simple cubic, body-centered cubic, and face-centered cubic. Each type has its own unique geometry which affects the properties of the solid. For example, metals like iron and copper have different unit cell structures, leading to differences in strength and conductivity. By studying these unit cells, chemists can predict and manipulate the behavior of material. Packing efficiency refers to how tightly the particles are packed in a solid. In some structures, particles are packed more efficiently, leaving less empty space. This efficiency affects the density and stability of the solid. For example, face-centered cubic structures have higher packing efficiency than simple cubic ones. Understanding packing efficiency helps explain why some materials are heavier or more robust than others, even if they're made of similar atoms. Ionic solids are made up of positive and negative ions held together by strong electrostatic forces. Table salt or sodium chloride is a classic example. The regular arrangement of ions in a lattice gives these solids high melting points and makes them brittle. When dissolved in water, ionic solids often break apart into their ions, allowing them to conduct electricity. Their unique properties make them essential in chemistry and everyday life. Covalent network solids are held together by a vast network of covalent bonds. Diamonds and quartz are famous examples. These solids are extremely hard and have very high melting points because breaking the structure requires breaking strong covalent bonds throughout the entire solid. Their unique bonding gives them remarkable properties, such as transparency in diamonds and piezoelectricity in quartz. These materials are crucial in technology and jewelry. Metallic solids are made up of metal atoms surrounded by a sea of delocalized electrons. This unique structure allows metals to conduct electricity and heat efficiently. The flexibility of the electron sea also makes metals malleable and ductile, meaning they can be shaped without breaking. Examples include copper, gold, and aluminum. The metallic bond is what gives these materials their characteristic luster and strength. Molecular solids are composed of molecules held together by relatively weak intermolecular forces, such as van der Waals forces or hydrogen bonds. Examples include ice, sugar, and dry ice. These solids tend to have lower melting points and are often softer compared to other types of solids. Their properties depend on the strength of the forces between the molecules, making them quite diverse in their behavior and uses. Solids exhibit a range of physical properties, including hardness, melting point, electrical conductivity, and solubility. These properties are determined by the type of particles and the forces holding them together. For instance, ionic solids are hard and brittle while metals are malleable and good conductors. By understanding these properties, chemists can choose the right material for a specific application, from building bridges to making computer chips. Not all solids conduct electricity. Metals are excellent conductors because their electrons can move freely. In contrast, ionic solids only conduct electricity when melted or dissolved in water, as their ions become mobile. Covalent network and molecular solids generally do not conduct electricity. This difference is crucial in designing electronic devices and understanding how materials behave in different environments. Solids also differ in how they conduct heat. Metals with their free-moving electrons are excellent thermal conductors. Other solids like ceramics or glass are poor conductors and are used as insulators. The ability to transfer heat efficiently or resist it is a key factor in choosing materials for specific uses, such as cookware or building insulation. Mechanical properties of solids such as hardness, brittleness, and malleability are determined by their internal structure. For example, diamonds are extremely hard due to their strong covalent bonds, while metals are malleable because of their flexible electron C. Understanding these properties helps engineers and designers select the right material for everything from jewelry to skyscrapers. Solubility refers to how well a solid dissolves in a liquid. Ionic solids like salt dissolve easily in water, while covalent network solids like diamond do not. The solubility of a solid depends on the nature of its particles and the solvent. This property is important in fields like medicine, where dissolving drugs efficiently can affect their effectiveness. Melting and boiling points of solids vary widely. Ionic and covalent network solids have high melting points due to strong bonds, while molecular solids melt at lower temperatures. Metals also tend to have high melting points, but there are exceptions. These differences are key in industrial processes where controlling temperature is crucial for manufacturing and material selection. Even in the most perfect crystals, defects can occur. These imperfections, such as vacancies or interstitials, can affect the properties of the solid. For example, defects can change the color of gemstones or influence the conductivity of semiconductors. Understanding and controlling defects is a major area of research in materials science, leading to new technologies and improved materials. Point defects are the simplest type of defect in a crystal. They include vacancies where an atom is missing and interstitials where an extra atom is squeezed into the structure. These tiny imperfections can have big effects, such as changing the electrical or optical properties of the material. By manipulating point defects, scientists can create materials with specific desirable characteristics. Line defects, also known as dislocations, occur when there is a misalignment in the rows of atoms within a crystal. These defects play a crucial role in determining the mechanical strength of materials. For example, the ability of metals to bend without breaking is largely due to the movement of dislocations. Controlling line defects is essential in developing stronger and more flexible materials. Surface defects occur at the boundaries of a crystal, such as grain boundaries or external surfaces. These defects can influence how a material interacts with its environment, affecting properties like corrosion resistance or catalytic activity. In nanotechnology and catalysis, controlling surface defects is key to designing materials with enhanced performance. Polymorphism refers to the ability of a solid to exist in more than one form or crystal structure. For example, carbon can exist as both diamond and graphite, each with very different properties. Polymorphism is important in pharmaceuticals, where different forms of a drug can have different effectiveness or stability. Understanding this phenomenon helps scientists design better materials for various applications. Allotropy is a special case of polymorphism, where an element can exist in different forms in the same physical state. Oxygen, for example, exists as O2 and O3 ozone, while carbon can be diamond, graphite, or fullerene. Each allotrope has unique properties, making them valuable for different uses. Allotropy is a fascinating aspect of solid-state chemistry, revealing the versatility of elements. Isomorphism occurs when two different compounds crystallize in the same structure. This phenomenon is common among salts and minerals. Isomorphism can affect the physical properties of materials and is important in geology and material science. By studying isomorphism, scientists can better understand the relationships between different substances and design new materials with tailored properties. Solid-state chemistry has countless applications in our daily lives. From the silicon chips in computers to the ceramics in cookware, understanding the properties of solids allows us to create better, more efficient products. Advances in solid-state chemistry have led to new materials for electronics, energy storage, and medicine. The field continues to drive innovation across industries. Semiconductors are materials with electrical conductivity between that of conductors and insulators. Silicon is the most widely used semiconductor, forming the backbone of modern electronics. By controlling the defects and impurities in silicon crystals, engineers can create devices like transistors and solar cells. The study of semiconductors is a major branch of solid-state chemistry and technology. Superconductors are special solids that conduct electricity with zero resistance at very low temperatures. This remarkable property allows for powerful magnets, efficient power transmission, and advanced medical imaging devices like MRI machines. Research into new superconducting materials is ongoing, with the goal of finding materials that work at higher temperatures for broader applications. Ceramics and glasses are important classes of solids with a wide range of uses. Ceramics are typically hard, heat-resistant, and used in everything from pottery to spacecraft. Glasses, being amorphous solids, are valued for their transparency and moldability. Both materials are essential in construction, technology, and art, showcasing the versatility of solid-state chemistry. Polymers are large molecules made up of repeating units, and many are solid at room temperature. Plastics, rubbers, and fibers are all examples of solid polymers. Their properties can be tailored by changing the structure of the polymer chains, making them useful in countless products from packaging to clothing. The study of solid polymers bridges chemistry, physics, and engineering. Nanomaterials are solids with structures on the nanometer scale. These materials often have unique properties such as increased strength, reactivity, or electrical conductivity. Applications include medicine, electronics, and energy. The ability to manipulate matter at the nanoscale is opening up new frontiers in solid-state chemistry and technology. Solid-state batteries use solid electrolytes instead of liquids, offering improved safety and energy density. These batteries are being developed for use in electric vehicles and portable electronics. The solid-state design reduces the risk of leaks and fires, making them a promising technology for the future of energy storage. Many solids exhibit magnetic properties, which are essential in data storage, motors, and medical devices. The arrangement of atoms and the presence of unpaired electrons determine whether a material is magnetic. Advances in solid-state chemistry have led to the development of powerful magnets and new magnetic materials for technology. Solids are also used to manipulate light in devices like lasers, fiber optics, and lenses. The way a solid interacts with light depends on its structure and composition. Solid-state chemistry enables the design of materials with specific optical properties, leading to advances in communication, imaging, and display technologies. Many catalysts are solids such as metals or metal oxides. These materials speed up chemical reactions without being consumed. Solid catalysts are used in everything from refining petroleum to making fertilizers. Their effectiveness depends on their surface structure and the presence of defects, making solid-state chemistry vital to industrial processes. Solid-state sensors detect changes in the environment, such as temperature, pressure, or chemical composition. These devices rely on the unique properties of solids to provide accurate and reliable measurements. Applications range from medical diagnostics to environmental monitoring, highlighting the practical impact of solid-state chemistry. Solid-state lighting, such as LEDs, has revolutionized the way we illuminate our world. These devices use semiconductors to produce light efficiently and with a long lifespan. Advances in solid-state chemistry have made LEDs brighter, more energy-efficient, and available in a range of colors, transforming everything from household lighting to large displays. Solid-state lasers use a solid material such as a crystal or glass as the gain medium. These lasers are used in medicine, industry, and research. Their reliability and ability to produce intense, focused beams of light make them invaluable tools in many fields. The development of new solid-state laser materials continues to expand their applications. Solid-state drives, SSDs, are a type of data storage device that use solid-state memory such as flash memory instead of spinning disks. SSDs are faster, more durable, and more energy-efficient than traditional hard drives. Their widespread adoption has transformed computing, making devices more responsive and reliable. Solid-state chemistry plays a crucial role in medicine, from the development of drug formulations to medical devices. The stability, solubility, and delivery of drugs often depend on their solid-state form. Advances in this field have led to better treatments and more effective pharmaceuticals, improving health outcomes worldwide. Study and application of solid-state chemistry have significant environmental implications. From developing cleaner energy sources to creating materials that reduce waste, solid-state chemistry is at the forefront of sustainability efforts. Innovations in this field are helping to address global challenges like pollution and resource conservation. The future of solid-state chemistry is bright, with ongoing research leading to new materials and technologies. From quantum computing to advanced batteries, the possibilities are endless. As our understanding of solids deepens, we can expect even more breakthroughs that will shape the way we live, work, and interact with the world. Let's recap what we've learned about the solid state in chemistry. Solids are defined by their rigid structure and fixed shape, with particles arranged in various patterns. Their properties depend on the type of bonding and structure, leading to a wide range of applications. From electronics to medicine, solid-state chemistry is a cornerstone of modern science and technology. Thank you for joining us on this journey through the solid state in chemistry. We've explored the structures, properties, and applications that make solids so important in our world. As science advances, solid-state chemistry will continue to unlock new possibilities, shaping the future in ways we can only imagine. Stay curious and keep exploring the wonders of chemistry.